to ensure that this binary code, for example, you have created a binary code for A, that should not match or that should not be confusing with any other binary code of any other letter. So whatever the binary code which you decide for A, it should be very clear and unambiguous, so that with the help of same binary code, you should be able to decode the text from binary code to text format. Now, you might ask me, sir, if you are asking me to create a binary code, you can ask me why not take ASCII representation, ASCII value of these letters itself. The problem with ASCII letters of this is that each character occupies around, for example, ASCII is 8 bytes. So I think not 8 bytes, it is 8 bits. Each ASCII takes 8 bits. So if the number of characters are less, and if I use ASCII information as a encoding for this, unnecessarily I would be occupying lot of unnecessary bits. So what I want a most efficient binary code for this, which means I want a binary code which represents A in its very unique format. Also, the process of finding binary codes for this character should be the most efficient approach. So how do we do that? So to do that, we use an algorithm proposed by Huffman, and that algorithm is called as Huffman coding algorithm. And under this, we have Huffman encoding as well as Huffman decoding. So let us try to look at that algorithm, which now, with the help of which we will be able to find this binary codes. Okay, once we are done with forming a binary codes for that, what we'll do is we will find out why this Huffman coding problem is always classified as a greedy method. It comes under greedy approach. That time we'll check why should we call this as greedy. What is that step where the decisions are being taken based on the greediness approach? So given this character text, let me do one thing. I'll delete this. So what we do is an input to algorithm. The input to algorithm is set of characters and frequency of characters in the text. Now, when I say frequency, what do you mean by frequency here? So input is somewhat similar to, let me give you an input here. So maybe you will find some input similar to this order. So input is in for example, I write A and I write frequency here. When I say frequency, I might write 10 here. And here when I write B, frequency is 5, frequency is 4, and then I write I, frequency is 1. It means that letter A has occurred 10 times in the text, for which we are trying to find a unique binary code for the letters which are composed by these alphabets. So after that, we might have Y, the frequency might be 12, and I think we can have Z as 2 and some B as 6. So assume that my text is composed of these letters, these 6 letters, and the text contains these letters for these amount of times. So I call this number here as frequency. So letter and a frequency. And input to my algorithm is this table. I mean, instead of calling table, this data, a letter and the frequency with which the letter occurs in the text. Sometimes some literatures and some books, instead of calling it as frequency, they also call it as weights. So weight can be interpreted as a frequency, and some books might even include this as a probability. The probability of character A occurring in that text. As you know, more the frequency, higher the probability of that character to occur in that text string. So given this input, what I need to find is, I need to find a unique binary code for A, B. So it should be A, Okay, so let me just repeat the same table. Okay, so now here we will include the code for each letter. So after once this is input to an algorithm, algorithm should give a code. Maybe for A you might give 010, for B you might give 10, for I it could be 110, some binary sequence. So my algorithm has to find out these binary codes, and that algorithm has to be most efficient, and that has to be most optimal as well. Fine. So let us look at that algorithm. How we going to work on that? So input algorithm set of characters frequency of this, and what will be output of algorithm? The output will be binary codes for each character. Okay. So far understood? You understood so far? Any questions so far? So it's very important that you understand what is input and what is output we are trying to get. No questions. Let me know if I need to proceed ahead. If no questions so far, then we will start working on algorithm. So see, let us start working on algorithm. The way the algorithm works is based on a tree-based approach. So what we do is we here always try to construct a tree, a binary tree, and based on that binary tree, we form the binary codes. So what do I do is I always pick up two characters which have minimum amount of frequency. Okay, what I do, I always pick up two characters which have minimum amount of frequency. In this case, what is that frequency? Can you list me out? What are those two characters? So I'll create few nodes here, then we'll properly construct the tree. So which are those characters? So from this, what I want, I initially select two such characters which have minimum type of frequency. Minimum frequency. What is that? I, which has frequency 1, and Z, which has frequency 2. So what I do is, I now construct a tree wherein these nodes are ordered in that order. For example, let us stick to this. For left side, we'll keep lesser value. So I'll keep it as 1, I, and what frequency it is with? 1. And for right side, I'll keep letter Z. What is the frequency of it? 2. So I construct these two nodes, and whenever I see, these are something called as, we call it as data nodes, means they are actually nodes which represent the characters and the frequency. What I do is I combine these two and I create a node, a root node, and I use square symbol to identify this. And what I do is I combine this both, and I'll call it as uh, root node for I comma j. And what is its weight? When I say root node for I comma j, what is its weight? Weight will be sum of these two. I mean, weight means the frequency. And I will use the word weight and frequency interchangeably. So the sum of this both the frequencies here would be 3. right? So when I create this node, a new entry in this table is formed, which is nothing but I comma j with frequency of 3. And whatever you have done, for example, I and j, this you have already visited. So now what I'll do is I'll just mark them as yellow. So I will no longer explore this. Oh, where is the color? Okay, so I have used I and Z. I already explored them. Okay, so let me also connect it by an actual tree format. Okay, done. Okay, now I need to repeat this process of selecting nodes from this table till I end up with a table which only contains one node in that. So initially I have selected I1 and Z2. Assume that I am removing them from the table. So if I do this with, if I highlight it with yellow color, just assume that I am removing them from the list. Or else let me, where is text? Okay, so let me just highlight it. Okay, so these are done. These are gone from the table. So these two have been gone from table, and I have added I and Z to 3. Now instead of making it yellow color, let me make it as normal one. Okay, we'll see it. So this is what we have done that. In next iteration, what you will do? In next iteration, you will again search for two remaining minimum. What are two remaining minimum? Now remember, you have to also count the newly added node as well. You have to also count the newly added node as well. So if you count the newly added node as well, what are next two minimum? Earlier 1 and 2, they have been removed and a new node was inserted in this table. So now what are remaining? So remaining is 10, 12, 6, 3 and 4. What is minimum? The minimum is 3 and 4. So this will be next, a tree will be constructed based on these two nodes. What is IZ3? I already have this 3. So this will be now, a sibling of this would be this node, which is B with frequency 4. So now I create a frequency 4 and I call it as B with 4, and they both create and they form an internal node. And for internal node, whenever I merge, I always try to show it in a square colored box. So it would be combination of I, Z, B, and what will be the total frequency for this? 3 plus 4, it is 7. So when you create that node as 3 plus 2, 7, this is how the new tree gets formed. So now once you have done that, these will be removed from this. For example, this will be removed here, and this B node 4 will also get removed. These are removed now, and let me make, so this you have already visited, so you will not explore them again. Okay, and this new node will be added again back to this. So I, Z, B, and what's the frequency? The cumulative frequency it gets is 7, right? After this, you will repeat the process till your table has one node. So what are next minimum here? I think something is wrong. I don't know why. How did we get this B here? I think if you already added B, let us make it as C. Okay, I hope you have observed what I think I have included. Um I have included B twice, right? So I'm just making it as, remember each character is unique here. We won't have multiple characters. So by mistake, we had B. You cannot have B here. It should be C. So some another character from whatever we had it. Okay. So this is done. Now, what are next two minimum nodes? The next two minimum nodes are 6 and 7. So 7 is already there. Let us keep 6 to the left of that. So let us keep 6. So left will be lesser than right sibling. So this would be C and 6. They both will be forming a root node, and so there is both will form a root node, and this will contain I, Z, B, C. What will the total frequency? 6 plus 7. What it is? 13. And this node will now be part of the new node. So what we have, this is already visited, and this is also been visited, and this I'll mark it with yellow color. Okay, so this is the structure as of now. So it is 13, and this will now be added as a new node to this I, Z, B, C, and it would effectively have a cumulative weight or frequency as 13. Let me know if I'm going wrong in addition. Okay, so now what are next two minimum? Okay, now here goes the tricky part. So I have done this right. Now what are next two minimum? I have 10, 12, and 13. Can you tell me what are next two minimum? A and Y. So A and Y both are your data nodes. So a new tree will be formed. So effectively now you are forming a forest. So you have this tree node here, which is minimum A with frequency 10. So you have to merge that. If it is there, you have to merge that. So A with 10 and Y with 12. So Y with 12. These both will get merged and they will form a new node here. What will be the value of this new node? It is A comma Y with a combined frequency of both, which is 22. Fine. So this node we have not yet removed. So this we have, but we have visited this both the nodes A and 10. We have visited this both nodes, and I'll highlight it with yellow color. Okay, we have visited this both. So now we have the current tree structure for this algorithm at current state of working. Okay, so now this node will get added to this. So A comma Y, and then we'll add 22 here. Yes. So now when we add this and when we repeat this process, which are next to minimum? These two. When these two are minimum, what I need to do is I need to directly add them. So to add them, I'll just use the same tree here. Remember, we are not creating a new node, and we will just use the square box. Remember, wherever you see this data nodes, I'm using rounded one. All internal nodes are square nodes. So here I'll be doing a combined addition of all. So what it would be? I, Z, B, C, and it will include A and Y. And here I have effectively considered all the characters. So what's an output here? It's 35. This is your final one. So this how you create a tree. And once you form the tree, now you can easily generate a binary coding. So to generate a binary coding, what we do is we start labeling left and right edge with some values. Okay, so let me create those values here. Okay. So we'll label left edge as 0 and right edge as 1. me create it. Okay, so what I have said, left edge is always marked with the label 0. So 0 here, and right edge is always marked as 1. So now I start labeling these edges. So it is 0. So wherever you see a left edge, just mark it with 0. And here is one left edge. So by now, I hope you started understanding how the binary codes are now formed. Okay, so did I label every edge in this tree? Yes. So if I label every edge in this tree, and this marks the completion of algorithm. So now, how do you find the binary codes? Can anyone guess how do we find the binary codes? I think from here onwards it's quite intuitive how to find a binary code for A. So if you want to find out a binary code for A, what you need to do is you need to traverse the tree till you find the node A. So if you want to traverse the node and when you want to find A, from root node you need to go to right and you need to go to left. So what it is? It would be right edge and left edge. So the binary code will be 1 0. So for B, if you look at B, where is your B in this? Here it is. So if you want to traverse to B, what you need to take? You need to take left edge, right, then right. So what it is? 0, 1, 1. And I, where is I here? I is here. So what would be binary code? 0, 1, 0, 0. What I told? 0, 1, 0, 0 for I. And for Y, where is Y here? So Y will be 1 1 because right node. Z, where is Z here? Okay, Z is here. You want binary code 0 1 0 1 0 1 0 1. B, I think it's not B, it's C. Where is C here? C is here. So it is 0 0. So these are called as Huffman codes for the following characters. So now if you want to send any message composed of these characters, what you do is you actually use the same binary coded symbols. So now if I want to send a message called as ABC, I want to send this message ABC. How would you translate this into binary coded format? What is code for A? 1 0. What is code for B? 0 1 1. And what is code for C? 0 0. So instead of sending ABC, now you will send this string. So this string is called as Huffman encoded string. Fine. This is for this. Now, for example, for decoding, how do I decode? If I get this value 1 0 0 1 1 0 0. Let us suppose at receiving side, someone who received this upon decoding. Now, if he wants to construct this ABC message back, how should he proceed? Can anyone get me a good logic for that? It should be fairly simple. So if I want to construct this string ABC back from that, what you need to do is you need to read these characters in the same order and you need to have this tree. So what I do is I'm reading 1, so I'm reading here, right? So 1 means I'll go here, then it is 0. Yes, 0 means I found a node, so I write A. Once I'm at A, now what is next binary string? The moment you got A, for next binary bits 0 1 1, you will once again start with root. So 0 1 and 1. So what is 0 1 1? You received a node. The moment you get a node, you print that character and you will start at the root node. So when you're once again when you're starting at root node, what it is? 0, 0. You will print immediately the moment you reach to this leaf nodes. You will print the character at that leaf node, and you put your pointer back to the root node, and you start scanning this nodes, right? So if I had a lot of another nodes, every time the process repeats, and that's how I reconstruct the code back again, and this is called as decoding. This is Huffman encoding, and this is called as Huffman decoding. And if you want to encode and decode, the decoding side should have this tree. So the essence of this algorithm is to construct this tree. And once this tree is constructed, rest all is simple. The binary codes, the encoding and decoding. So I hope you understood how we have done that. So for example, this you will once again, when did we stop our algorithm? When we have considered all these nodes, and when I have only one node to process, which is this marks the end of our algorithm. Should be 35. Okay, so only one node I have, that's where my algorithm stops. So this is called as Huffman encoding. I find out binary codes and that. Now look at this. If you look at this, what do you find a similarity between length of binary codes and frequency of these characters? Do you find any relation, the length of binary code and frequency of these characters in that? What pattern or what relation you find? The length of binary code and the frequency of letter in the original input. Can you tell me what relation you are able to find that? So I'm waiting for your responses. What relation is do are we finding it? Am I audible? I'm not getting any response. Am I audible? One's complement of its frequency binary. Hmm. Okay. Do you think that it is a complement of binary? Maybe that's a good observation, but assume that A has frequency of 100. If A has a frequency of 100, still this will not affect. So it is not going on binary one. Still, any even further more detailed observation? What observation you find between the length of binary code? I'm not asking binary pattern, but length of binary code and the frequency of that letter in the original character stream. So have you understood this first? I think I'm not getting any response. Maybe you might have not understood, or is there something wrong? Let me know. So the basic relation between this is more the frequency of a letter, less the length of binary code. That's the relation. I hope now you can observe that. If a letter has higher frequency, it will has a lesser length of binary code. Because if I have a text, if I have a text and you are asked to find this Huffman encoded string. For A, you have to find out the binary code. So you have to search where is A inside this. So assume that if I keep this A at the bottom of that, and every time you have to do a more depth traversal, more the do you do the depth traversal, more the computations. So this entire Huffman encoding, it tries to give a least binary encoding for a character which is of higher frequency. It means that when you are encoding, you are more likely to encounter character A as compared to character I, because I is less, so probability of A occurring is high. So probably it makes much more sense that I keep this A node at the top of node, so that with one retrieval operation, with one traversal operation, I should be able to get A, so that I can easily construct the binary code for that. So that's an internal approach. And based on that approach, the entire algorithm is considered to be a greedy one. So here the greediness is that we always go for minimum. We want to keep the nodes which has a lesser frequency at the bottom of the tree. So you want to keep a bottom of the tree, we always start with minimum nodes. So that we assume that when I reach to the root node, a nodes which has a higher frequency tend to be near to the root. So when I want to retrieve something from this, I can quickly retrieve. And the characters which occur more number of times, they make sense to be at upper level of root nodes, because with a few amount of traversal I can quickly retrieve the code. So that was the intention based on which this algorithm called as greedy one. But when you go for real-time implementation, once you find these codes here, you can store it in another table with additional space complexity, and you can quickly retrieve the code. But the main purpose for which this Huffman encoding is called as greedy approach is because of minimizing the length for the characters of higher frequency. And how do we do that? By constructing tree from bottom up approach. Here if you look at this, we are constructing tree from bottom side. Okay, have you understood? Have you understood the approach, the entire approach? What is Huffman encoding, Huffman decoding? Okay. So before I leave this lecture, I'm not sure why you are not responsive today. Is there anything side by side going on, any event or something? Or you are angry that the Python ISC test was difficult? Okay, so we'll see what we'll discuss that Python problem on some other day. So I hope you understood that. Now, the next challenge is to implement an algorithm for this in Python. So let us see. I'll be looking at that implementation in next lecture, but I would be glad to have any idea of implementation, what data structure, what it is. If that discussion happens in the Telegram group, I would be happy to give additional inputs to you there as well. Okay. So yeah, I'll end this lecture. So let us meet in next lecture to look at the implementation of this Huffman coding. And by that time, just be ready with some basic understanding of how we can implement. Just think of multiple ways we'll implement on that day. Okay, you can leave